Hi everybody, my name is Gareth and my aim is to give you some confidence with biochemical calculations, specifically by helping you ditch any approach where you plug and chug numbers into equations, rote-learned equations particularly, and instead learn how to visualize the flow of the numbers and do simple arithmetic to follow the mole. So just to reflect on whether you need this approach, think about how you cope with these scenarios here. So doing a simple quantity, moles of glucose in a certain amount of a particular solution, maybe just knowing the amount of moles in a certain quantity, a certain weight of the glucose. What about doing a mixture, adding glucose solutions together, or something quite simple like doing dilutions, adding glucose to water? What about multi-component solutions, adding the glucose to something that's already got other compounds in, like sodium chloride? Other concentration terms, very common to use weight per volume per volume, grams per deciliter. And then there's loads of chemicals where you have to deal with density as well. So lots of different ways in which calculations can be quite tricky. We're going to start today just looking at the real simple quantity one, just moles of glucose in a certain solution. Now, you're probably used from your training at school and other courses to think in terms of equations, think in terms of these C1 V1s and CVs and things, but they really do create a disconnect for you. They're often incorrectly done. We see people putting the wrong thing on the wrong side of these equations a lot. And that's because it's a very abstract approach. You really are relying on the fact that you get the input right, and then this sort of black box of these equations in your calculator produces the right output. Not only does it often not work, but you're often in a position where you're not empowered to know that it hasn't worked. So your discernment as to what the result should be is often not there. What I'm going to try and encourage you to do is to form a visual connection between all the things in a process, to really think about the flow of quantity from one vessel to another, and to visualize what is actually in each vessel, to think in terms of volumes that are sensible for the context. And all the way through, we'll be doing simple arithmetic. We won't be doing maths, we won't be doing scary stuff. We will, however, be using lots of sensible numbers. So we'll be using prefixes like milli and giga and million and things like that, things that you use every day in life. You don't use scientific notation in everyday life. You use prefixes that make numbers sensible. And most important of all, we'll be following quantities. We'll be keeping a track of things. We humans are brilliant at keeping track of objects and items like cash and dogs and cars. We're not good at keeping track of abstract quantities like concentration. So these are the sort of three foundations of the approach. So here's the problem that we're going to cover in this session. 200 microliters of 0.5 millimolar glucose. How many moles of glucose are in that? Well, we're going to start by thinking about what this 0.5 millimolar means. So let's deconstruct this 0.5 millimolar. Let's express it in plain English. What it means, of course, and I'm sure no one has a problem with this, that it's 0.5 millimoles in a litre. Here's a litre. It's 0.5 millimoles in there. Now, what about a bit less than that? What about a mil? So what about if we just took a mil of that solution? There'd be 1,000 times less. So there'd be 0.5 micromoles. See these scales that we're working with here? Litres going to milliliters, millimoles going to micromoles. And of course, we can take it one step further. We can go zero point 0.5 nanomoles in a microliter. So here's a microliter in this little pipette tip. That microliter has 1,000 times less than the mil. So there's a nanomole in there. Now what we've done through this is we've deconstructed this concentration term into an amount per volume. And furthermore, the volume that we're thinking about is directly relevant to the volume that we've been challenged with in the question. And now we're going to express it in plain English. We're going to say every microliter contains half a nanomole or 0.5 nanomoles. So now it's trivial to say if every microliter contains half, 200 microliters must contain 100 nanomoles. So we haven't used any equations here. We've just done a flow of logic. We've used sensible numbers, and we've got to an answer that we can discern is correct. Now let's try it with the plug and chug method. So the equation that everybody knows, of course, is N equals CV, concentration times volume. The first thing we have to do to apply this equation is we've actually got to do some deconstruction. We've got to take the concentration, 0.5 millimolar, and we've got to express it in scientific notation. Now that is a bit of a task for some people anyway. Same with the volume, expressing the 200 microliters as 200 times 10 to the minus 6 liters. Now these prefixes, these scientific notations here are quite friendly because they are in the milli and micro sort of range, -3, -6. Multiply them together, again, not totally trivial for everybody, and we get a nice answer, 100 times 10 to the minus 9 moles, which of course is the right answer. We already know that from the previous thing. And the other thing is that we do have some nice numbers here, but what we don't have is any sort of visual fix anymore. We've sort of lost that nice tracking that we had before. We've gone into equation land, scientific notation, numbers that aren't particularly easy to discern. The thing that's made it a bit easier for us though is that we do at least have these nice -3, -6, -9 indices, and they of course are milli, micro, nano. So that was quite kind to us. Not all solutions are going to be that kind. And in fact, students can get themselves tied up with knots with this one, even though it's as simple as I showed you before, because they can start doing what is actually quite a sensible thing and constructing the 0.5 millimolar as 5 times 10 to the minus 4 and the volume, 200 microliters, as 2 times 10 to the minus 4. Now this is all fine and you can still do the sum, but what you get at the end, 10 times 10 to the minus 8, although we know it's 100 nanomoles, you'd be surprised at how many people get this the wrong way round. They either say it's 1 nanomole or it's 1 times 10 to the minus 7 or something like that. So not only have we lost the visual flow, but we've really gone into black box land because we haven't got those nice -3, -6, -9 indices. Now where the wheels really fall off the bus is where students try and mix the approaches. So they've got the 0.5 millimolar kept as millimoles per litre, but then they get into scientific notation land with the volume. And this sort of mixed units is absolutely horrendous, but we see it all the time. And it's really, really common with complex problems where you've got lots of different volumes and mixtures all compounding this, this confusion. So just to go back to the nice way of doing it, remember what we did was we deconstructed the 0.5 millimolar, we expressed it as moles per volume. We then went through the scales. We used milli, micro, nano, litre, milliliter, microliter. And the aim was to get to a volume that was relevant to the context. We really wanted to be in microliters because that's what we were going to be dealing with in the problem. And we expressed everything in plain English. Very, very simple statement that a child could understand. Every microliter contains 0.5 nanomoles, and then it was very easy to come up with the answer at the end. So let me know what you think about that approach. Are you someone that uses the formula? Are you someone that likes doing the scientific notation? Has it ever got you into problems? Do you think you could give this a go? Let me know and we'll have another lesson very soon.